Hello everyone, welcome to the webinar. My name is Piyush. I work as a project engineer at AECOM India in its Gurgaon office. Today's topic of discussion is design of three-span continuous PSC box girder bridge constructed using cantilever construction technique. This is actually a case study of a bridge, balanced cantilever bridge that we had designed at AECOM for Delhi Metro, Phase 3, Line 7. So this is what I will take you through in this webinar. First, I'll give you the general description wherein I'll tell you about the project, the overall brief of the project. Then, what are the problems? What were the design actions that we considered for the design? The design actions. What are the different kind of loads that were considered for the design of the bridge? And finally, having defined the design action, we'll go to the structure analysis, the tools that we used and how we use the tools to actually design our structure, and finally we'll come to the results. So this is actually a project for Delhi Metro Phase 3 Line 7 that we designed for the contractor, and the bridge is actually under construction. Actually, 90% of the bridge has already been constructed. Only the superimposed dead load, the SIDL part remains. As you can see on the screen, right side on the screen, this is actually an image from the site. This is actually an image. So this is actually an image from the site. 90% of the construction is already over. So we'll try to explain uh, the different parts with the help of the actual images from the pictures from the site. So as I already told, this is a part of Delhi Metro Phase 3 Line 7, and the span configuration is 34 meter plus 60 meter plus 34 meter, and the structure type is actually cast in situ PSC box girder. And actually you see these are the three spans for this structure. We can see only two piers. So the first span, if you can follow the mouse, the first span is 34 meter, the mid span is 60 meter, and then the last span is again 34 meter. Now the area below the end spans, this area and then this area, this is available to us all around the year for construction. So what we are doing, we are casting the end spans, the first span and the last span, on the ground supported staging. And this part here, you see, this is Nazargarh drain, and the bridge is actually crossing it, and it is the mid span is actually 60 meter, and this part is actually cast with the help of the form trailer using cantilever construction technique. We'll see the detail of the construction sequence in the subsequent slides. So as I told you, this is a three-span structure, P121 to 122. This is Pier 1 P121. This is Pier 122. This is Pier P123, and this is Pier P124. So the span between P121 and P122 is 34 meter. Span between P122 and 123 is 60 meter, and finally the span between P123 and P124 is 34 meter again. So as I already told you, this part, the 34 meter span, the end spans are cast on the ground supported staging, because we have this zone. This part is available for the staging all around the area. The central span, the 60 meter span, this is actually cast with the help of the form trailer, segment by segment. And the entire structure is cast in situ, PSC box girder bridge. And as you can see on the plan, the bridge is straight. There is no curvature in the bridge, and P121 and P124 are free piers. We are providing the free bearings here on P124 and P121, whereas P122 and P123 are integral piers. And as you can see in the elevation and the plan also, uh, this P122 and P123 are twin piers, twin leaf type piers. And as far as the foundation is concerned, we are using 6 pile group for the end piers P121 and P124, and 8 pile group for the integral piers or the intermediate piers P122 and P123. So coming to the cross section of the box girder, the overall width of the deck is 8.844 meter. As you can see, this is a bridge of Delhi Metro. It is supporting two tracks, one for the up and one for the down line. Then we have parapet. So the distance of the center line of the track with the center line from the center line of the box is 2.05 meter. Overall depth of the box girder varies from 5 meter at the pier location to 2.1 meter at the midspan. At the pier location, the web thickness we have used is 550 mm. The soffit thickness is 500 mm. Whereas at the midspan, we have used 300 mm thick web and 300 mm thick soffit. The overall area of the box near the pier is 8.89 meters square, and the moment of inertia about the y-axis, this is y-axis, is 28.79, whereas the area of the smallest section of which is of 2.1 meter depth is 4.98 meters square, and the moment of inertia about y-axis is 2.63. And the width of the soffit throughout is 3.4 meter. Coming to the piers and the foundation, as I already told you, the intermediate piers P122 and P123 are integral piers. These are twin piers. Each leaf is of the dimension 1000 mm by 3400 mm. You can see a cross section to 1000 mm along the longitudinal direction and 3.4 meter along the transverse direction. Now, why we have used twin pier? Because the twin pier gives the flexibility to the structure. So the time period of the structure, overall structure, will increase, and we'll see in subsequent slides the moment of the response of the structure actually for the reduced time period will be lesser. Then we have free bearings at P121 and P124, which are circular piers of 2.1 meter dia, and throughout we are using 100 mm dia cast in situ board piles, and we are using 6 pile group for end piers and 8 pile group for intermediate piers. And normally the depth of these piles vary from 25 meter to 30 meter. And because these piles, this foundation is actually near the Nazarwar drain, we have used submerged capacity of the soil. We have used submerged capacity of the soil for the analysis purpose. Material grades for the cast in situ box sections, we have used M55 at most of the part and M60 at the selected few locations. For all the piers, we have used M50 grade concrete, and for the pile and the pile cap, we used M35 grade. The pre-stressing steel, we have the Young's modulus is 195,000 MPa. Strands, we have used the nominal dia of the strands that we have used is 15.2 mm with the area of 140 mm square, and it is class 2 low relaxation uncoated stress sleeve tendons. The breaking strength of the strand is 260.7 kN, which corresponds to the UTS of 1860 MPa, and the jacking stress is 3095 MPa. The anchorage set in, the slip at the anchorages is 6 mm. The wobble friction factor that we have considered is 0.003 per meter, and the curvature friction is 0.2 per radian. Now coming to the construction sequence. As I already told you, the end spans, which are P121 to P122, P121 to P122, and P123 to P124. These end spans are cast on the ground supported staging. So because this part right beneath the span, 34-meter spans, is available to us for the ground supported staging. So we are casting these end spans first on the ground supported staging. Then we anchor a top tendon. We'll see in the subsequent slides why we are anchoring a top tendon at this stage, uh, which uh, which which continues from this node number 201 right up to the segment on P121. After that, we are not removing the ground supported staging. We are casting segment S1. Actually, we are mounting the form trailer first. Then, with the help of this form trailer, we are casting segment S1 on both the sides. So, we are casting segment S1 on both the sides. Then, after casting segment S1 and after the concrete has gained its strength, 80% strength or 35 MP, whichever is later, or sorry, the 3 days, whichever is later, we stress the top tendon, the top cable, the cantilever cable. Then we move the form traveler from this location onto the segment S1, and now we cast segment S2 on both the sides, and then we'll stretch the cable, top cable. Then again we move the form traveler to cast the new segment, and this is how we'll go on to cast all these cantilever segments. Now what is happening? Now we could have removed this ground supported staging at this stage only. But now if we remove the ground supported staging at this stage, we will have huge sagging moment in this part. Now when the structure is completed, let's say when we cast the stitch segment and when it is a continuous structure, the bending moment due to self weight in this part will actually reduce. So we'll have to provide the tendons at the bottom fiber for a short while for the temporary stage, for this temporary stage. So what we are doing, we are keeping this ground supported staging until few stages more, so that we cast enough number of these segments on the cantilever sides so that the sagging moment at this part mitigates, and the requirement of the bottom tendons in this zone is bare minimum. So after casting segment S8 or up to 23.5 meter from the P of P122 and 123, we see that the sagging moment due to self weight has mitigated enough. So what we do, we stress some of the bottom cables, and then we remove the ground supported staging, and then we continue with our cantilever construction. Moving ahead, finally when we reach the stitch segment, we try to match the level of the two cantilever tips, and then we cast the stitch segment with the help of a suspender which is supported on both these cantilever arms. And just so you know, the quality of construction and the precision was, and the construction was of so much of precision and accuracy that the differential deflection between the two cantilever tips was only 3 mm. And thus after casting the stitch segment, we stress the bottom cables in the central, in the mid span, and then after putting the SIDL, the parapets and the plinth, we open for the traffic. So this is actual picture from the site. We are casting segment S8 with the help of the form traveler on each of the side. This form traveler is supported on the previous segment. It is actually clamped. So this is a segment just before the stitch segment. So after casting this segment, we'll stress the top cable from this new segment up to the pier and up to the segments on the back, and then we move the form traveler. Will suspend the suspender here, which will with the help of which we'll cast the stitch segment. So this is the suspender here. Now we are casting the stitch segment with the help of this suspender. After the concrete will gain its strength, we'll stress the bottom cables here in the central span, and then we remove the suspender and the form tables. Now coming to the design actions that we considered for the design of the structure. So we considered the permanent actions such as the self weight of the concrete, the SIDL, superimposed dead load. The permanent action also include the effect of creep and shrinkage, the wind and the thermal action, the live load, the seismic load. Delhi is in seismic zone 4. So not only did we consider uh, seismic along longitudinal and transverse direction, we also considered seismic along the vertical direction. Since it is a continuous structure, we need to consider the differential settlement between the different foundations. We also need to consider the secondary effects of the creep, shrinkage, and fill stressing. Not only that, we also need to design our structure, check our structure actually for the construction load. Now what you see on the screen here is the form trailer. Now this form trailer is causing not only the vertical load, but also it is because of the form trailer we have some moment on this segment. Now each of the segment needs to be checked for the load of the form trailer. Not only that, we also need to consider the accidental form of the form trailer along with the segment. So at times for the substructure for the piers, this accidental for the form trailer may be the governing case. So the permanent action, the self-weight of the component, the concrete we have taken 2.5 ton per meter cube, and steel we have taken 7.85 ton per meter cube. The SIDL, it is a metro bridge, so we have parapet of 3.26 ton per meter, then handrails, rail and parrots, cables, the plinth of 3.4 meter, then other items, and it sums up to 8.5 ton per meter. We also need to design for the thermal action. So we consider overall temperature variation in the structure and also the differential temperature. Now we have performed this thermal analysis, and the entire analysis actually we have performed using MIDAS with the software. We'll see that in subsequent slides. Live load, uh, the live load has been given to us by Delhi Metro. We have designed the structure for 6 bogie or 4 bogie train, whichever causes the maximum or the worst effect. So each bogie is having 4 axles as shown in the screen, and each of the axle weighs 17 tons. Length of each bogie or each car is 22.1 meter. Now we have two cases. I mean, uh, we have two sets of value for A, B, C, and we need to consider that for the design. Apart from this vertical load, we also need to design our structure, consider the effect of the horizontal effect of this load, the braking and the traction. Braking we have considered 18% of the unfactored vertical load, and the traction we have considered 20% of the unfactored vertical load. Now, to have the worst effect, we have to consider braking in one direction and the traction in the other direction. So both of these will add up, and this will be 38% of the axle load. Additionally, we need to include consider impact factor of 4.2 for longitudinal analysis and 1.67 for transverse analysis. As I told you, this is the structure. The structure is in Delhi, which is very high seismic zone. So we have performed response spectrum analysis, and we have considered seismic forces along longitudinal direction, transverse direction, and also the vertical direction. So some of the parameters for defining the design spectrum is zone factor, which is 0.24 for Delhi. Importance factor of the bridge is 1.5. Soil type is type 2 medium. And to find out the time period and the frequency of the various modes, we have performed eigenvalue analysis. Now this is a continuous structure, so we also need to perform differential settlement because the redundancy would cause the additional stress in the structure. So we have considered 12 mm settlement in the long term and 6 mm settlement in the short term. Then we also need to consider the secondary effect of the creep, shrinkage and pre-stressing. Mainly because our structure is indeterminate. It is a 3-span continuous base, so the secondary effect of creep, shrinkage and pre-stressing will be used. Now when we see our structure, actually it is a cantilever construction. In the first few stages of the construction, when we cast the first few segments, I mean just before the casting the stitch segment, our structure is not indeterminate. Until that time the structure is determinate. So there will be no secondary effect of the creep, shrinkage and pre-stressing until the casting of the stitch segment. So almost all the cantilever tendons will not have any secondary effect. We are stressing only the bottom cables after the casting of stitch segment. So only those cables will have the secondary effect, because only after casting the stitch segment structure becomes indeterminate. So it's very important to consider the actual sequence of loading and the actual sequence of the construction. And this we have been able to do with the help of MIDAS Civil to simulate the actual construction sequence on the software itself and see the effect of the sequence of loading versus the sequence of construction on the software. Now coming to the analysis part, we created numerical line model. So all these pictures you see on the screen will be actually from the actual site. So we created numerical line model. We performed the line beam model. So for superstructure or the box girder and the piers and the piles, we have used line elements, a 2D element, one direction element. Sorry. The pile caps have been modeled as plate elements. This pier also have been modeled as line element or the beam element. So here you see a 3D structure and you'll see the line structure, the numerical line model. And to this line, actually, we have defined the cross section property for this cross section. All these cross sections can be either defined in MIDAS Civil itself, or we can also import this cross section from AutoCAD. The substructure, as I already told, the pile and the piers have been modeled as line element, and the pile cap has been modeled as the plate element. To simulate the effect of the soil, we have provided soil springs, and we have used different stiffness of the soil for static case and the dynamic case. Concrete has been modeled with the help using the time-dependent material property in the software. We have defined this creep coefficient graph. If you can see on the screen, this is a creep coefficient graph along with the time, shrinkage coefficient graph, strain graph with respect to time, and this compressive strength, how the concrete is gaining the compressive strength with respect to time. This we have defined as per CBF5P, which is inbuilt in MIDAS Civil. So coming to the pre-stressing analysis, we have used internal pre-stressing. We have used two kind of jacks, 19 to 15 or 12 to 15 kind of anchorages. Now you see the cross section at the pier. These are all the top cables, the cantilever cables, and this is the cross section at the mid span. These are all the bottom cables. All the cables are jacked or stressed from one end only. let's go to the pre-stressing drawing and see. Uh, let's see the pre-stressing, the tendons that we have defined. So these are our span actually. It is symmetrical about the mid span. So this is the end span. This is the central span. This span is cast with the help of the form traveler, with the help of the ground supported staging, and this part is cast using the form traveler. So what we do, first of all, we are casting this part, the end span, up to this part. So what we do, while there's still ground supported staging, we are stressing this cable number one. This cable number one at the top, you can see it is from node number 201. These are the node numbers. Node number 201 up to the pier, up to the segment at the pier, the diaphragm at the pier P121. Now after this has gone, this part of the concrete has gained its strength. We are mounting the form trailer on this pier head, and with the help of the form trailer, we are casting this segment. Now after this segment has gained its strength, we are stressing cable number 2, which is running from node number 202 up to the node number 101. Then we move the form trailer from this segment up to onto this segment, and then we cast this segment. This is segment S1, this is segment S2. We cast the segment S2, and then we stress cable number 3, which runs from node number 203 right up to node number 102. Now the question is why we are stressing the cable number 1. This cable we are providing right from this P121 up to P121. Now this entire span is cast at one time on the ground supported staging. Now when we are stressing this cable number 2, there will be high compressive strength in this part. Now there is a fear of tensile, there is a fear of crack here at this node 101. So we need to have high compressive force in this part, and actually this problem will be there for each of the tendons at each of these segments. So we need to have high compressive stress at all these nodes, at all these fibers, so that there is no splitting tendons when, let's say, cable number 4 is stressed. There is no splitting tendon when cable number 5 is stressed. Another thing to notice is that when we show you the cross section, let's say for the cable number 2, which is running from node number 202 to node number 101. So this is node number 202, this is cable number 2. So we are stressing the cable number 202 at we are stressing the cable number 2 at node number 202, and we are stressing the cable, we are keeping the cable at the haunch. While when we see the section of node number 101, so the node number 101 is in the first span, in the end span, which is caused from the ground support staging. So and we are anchoring this cable in the blister. Now when we see our structure, the end span is cast at one time, so this face is not available to us, not the web. So we have to take the cable down to the blister, while on the other side, the cantilever side, we have these faces are available. So we are stressing these cables on the face of the haunch itself, while the cables are stressed or anchored in the blister on the end span. So trying to explain with the help of this diagram of this picture. So this entire segments are cast on the ground supported staging at the same time. So the face of the concrete or the haunch is not available at these nodes. But let's say this is segment S1 and this is segment S2. We first cast segment S1 After that we'll be casting segment S2, then we'll be casting segment S3. So before casting segment S2, we have this the face of this segment S1 available. So we are stretching the cable to the face itself at the horns, and while we are taking the cable to the blister on node number 101. Another thing to notice is that at the central span we have so many bottom cables. So 5 pairs of cables at the central span. While at the mid span, while at the end span we have only 2 pairs of the cable, 13, 12 and 13. So as I tried to explain you during the construction sequence slide, why we kept the ground supported staging until let's say until the 23-meter of the cantilever span was cast. So with the help of, because of that construction sequence, we were able to achieve we were able to optimize the number of tendons at the end span. Otherwise we would be requiring somewhere around 4 tendons in this span. Coming back to our slide, so these are the images from the pictures from the site. This is the zone which is cast on the ground supported staging, and these are the zones. So this space we see it is available to us. So cables can be stressed if we have to stress a cable. Let's say this is cable number 1. It can be stressed on the face of the concrete itself. While on this part, on the end span, we'll have to take the cable into the blisters and jack them. So these are the blisters from the site. Now the construction sequence which I explained in the previous slides were actually simulated on MIDAS Civil, and we were able to perform the actual construction stage analysis in the software itself. Now before going ahead, uh, just so you know, this is not a typical balanced cantilever construction, hence the term cantilever construction technique. So we are casting the entire span at one go, then we are casting these segments one by one with the help of cantilever construction technique. We have defined these temporary supports. These are compression only springs to simulate the ground supported staging on this part. And we are keeping the ground supported staging until a few segments, let's say after 20 until 23 meter of the cantilever has been cast. Then we are removing this part. In the software itself, we have also taken the load or the effect of the construction loads. The form trailer, the load of the form trailer is 50.4 ton given to us by the contractor, and we have also applied the moment which is caused by the eccentricity of the form traveler, eccentricity of the center of gravity of the form traveler. Coming to the results, now we can see, as I told you, now because of the effect of this ground supported staging, we don't have any sagging moment in this zone. Now, this is a bending moment diagram due to self-weight during the construction, and this shear force diagram due to the self-weight of the structure during the construction. Now, had we removed this temporary support, we would have this significant amount of sagging moment, for which we would have to again provide the tendons, which would be just a temporary stage. Now, this is the only sagging moment left when we have cast this 23 meter of the cantilever segment and removed the ground supported staging. So if you see the value, the bending moment at this part is 562 ton meter, while at the end span, while at the intermediate pier we have around 3700 ton meter. This is bending moment diagram after the stitch segment has been cast. Now another point I want to make is why we need to perform actual construction sequence analysis. Now let's try to imagine what would be the bending moment diagram due to self weight had the entire structure entire structure been cast at one go. We would have some sagging moment here, and then we would have some sagging moment here itself, here also. But because of the construction sequence, the stresses are locked, and due to the self weight of the structure will not have any sagging moment in this zone. Now the variation of the bending moment diagram with each construction stage. The red line shows you the variation of the bending moment diagram at node number 106. This is node number 106. So this is mostly near zero only. I mean, at some time it's go up to uh, goes for sagging, and then it's mostly hogging in this part, and which is again a nominal value. And the green line shows you the variation of the bending moment at node number 8. So we have hogging moment. So at node number 8 we'll always have this hanging moment. Now let's see how it increases. This is the increase. This is because of uh, casting of each of the segment. Now as we go further, the bending moment, it increases. So as we go further, because of the lever arm, the increase in the bending moment is greater. A bending moment and shear force envelope due to live load. Live load analysis is performed in MIDAS Civil with the help of influence line diagram. So for each of the element, for each of the load effect, the bending moment, the stresses, the shear force, the deflection, the MIDAS, the program will create the influence line diagram, and based on that, it will place the vehicle to cause the maximum and the minimum effect. So this is the bending moment envelope, and this is shear force envelope. Now coming to the pre-stressing, this is one of the pre-stressing loss graph, not the loss actually, the effective pre-stressing tendon for a particular cable. Let's say cable number 10, which is a cantilever tendon at the last stage, and this is a distance, and this is the effective tendon force which remains in the cable. Now what we can see actually is in this zone, since I've already mentioned all the cables have been staged from one end only. In this zone, we can very clearly see there is a loss, high loss. So we can very well make out that in this zone, this cable has been stretched from this end, and this loss is because of the anchor slip. So there must be a null point somewhere here. So beyond this point, we again have a drop in the continuous drop in the tendon, which is because of the friction loss. So this was just one example. This graph was actually taken from MIDAS level itself, which gives the overall picture of the tendon force, and we can just from look we can we can capture the overall image of the tendon and the losses. Stress check. It's very important to for as per the Indian codes, we have some allowable stress values for the structure, and for the bridges, we do not allow any tension at the top of the bottom fiber. While we do allow some tensile value, some tensile stress value at the bottom of the top fiber during the construction. So this is a we have tabulated the values. So at the transfer and the construction stage, for the dead load and the SID, whatever load is there, we we only allow until up to 1 MPa of tension at the top or at the bottom fiber. While the compressive strength we allow up to 0.4 FCK or 0.5 FCJ. FCJ means the strength of the concrete at the stage or at the day of stressing. So whichever is lesser. So we have 22 MPa allowable compressive strength for M55 and 24 MPa for M60. While doing the service, for case 1, normal case, the allowable compressive strength is 22 MPa for M50 and 60 MPa for 24 MPa for M60. While do not allow any tension at the top or even at the bottom fiber. Same likewise for the seismic case, the allowable compressive strength and the allowable tensile strength. Then G3, which is a temperature fall case, we allow some tension which is less than the modulus of rupture or the tensile strength of the concrete. This is mostly because this is cast in situ structure, so we can rely on the dowel action. So we can rely on the dowel action for the temperature. So the some of the stress check images taken from the software itself. Stage 1, when we still have the ground supported staging. This is the stress at the top fiber due to dead load, erection load, and the effective pre-stressing until this stage. At this stage, so at the top fiber we can see the negative value of the stress is compression and the positive value shows tension. So the entire structure, the top fiber for the entire span is under compression. The minimum compression is 0.45 MPa at stage number 1, while at the bottom fiber we have slight tension which is 0.16 MPa at the first stage. After similarly, we need to check these stresses at all the span, at all the stages, at the top and the bottom fiber. Now stresses at the top fiber due to after 120 years, after 120 years, but no live load. So we have the effect of dead load, SIDL, and effective pre-stressing. After 120 years, I mean, whatever losses due to creeps, shrinkage, relaxation have taken place, we have to subtract that, and this is the stress at the top fiber after 120 years. So we have residual compression of 1.07 MPa at the top fiber, and which is at the end diaphragms only. And mind it, this is without live load. And similarly, at the bottom fiber, we have a residual compression of 4.15 MPa, which is near this segments or near the intermediate pier. Now checking the stresses for the service loads, normal cases, that is just the permanent loads and the live load with the factors which has been defined in the DBR design basis report. So at the stresses at the top fiber, due to load combination G1 normal case, we have a compression, overall compression of 1.02 MPa, and we have an overall compression of 0.87 MPa at the bottom fiber, which is actually at the stitch part. And this is after 120 years along with the live load. And when I say live load, I mean it considers 1.2 impact factor, and also uh, the load factor, additional load factor, which is due to which is for the live load. For the seismic case, again overall we can see our structure is under compression at the top fiber and at the bottom fiber. And moreover, in the seismic case, in the longitudinal direction, this part, because the structure is uh, integral in this part, we have a frame. The action will be frame. And moreover, in this part only, for the longitudinal seismic case, there will be reversal of the stresses due to seismic case. Once when the uh, once when the seismic force is from left to right, and then again when from right to left. In one case, we'll have the tension at the top. In another case, we'll have tension at the bottom. So we need to consider both of them while designing the structure. Now, creep and shrinkage plays very important role in the design of a structure like balanced cantilever construction. Now, why? I see this is a pre-camber graph which we have taken from the software. Now we provide this pre-camber so that after a desired time, let's say after 120 years or maybe after 20 years, which is actually a call of the engineer in charge. So after some time, you want to have a perfectly horizontal or the desired profile of the structure. Now the effect of creep is actually in the direction of the permanent load. Now, if let's say we have a simply supported structure which sags in under the effect of all the permanent loads, the effect of creep will be to increase that sagging or the downward deflection of the structure. But if the overall effect of the permanent loads is hogging, the that is it deflects the structure upwards, then the effect of the creep will be to continue the deflection upward. Now this is our structure, the camber control graph, the camber that we provided for our structure. So this point denotes P121, and somewhere here we have the first integral P122. This is the zone of stitch segment. Somewhere here we have P123, and this is here we have P124. Now what is happening? This is the camber control graph. That is, this is the point. This is the camber that we need to provide at the stitch segment. So we need to cast stitch segment actually 6 mm below its actual level. Now why it is happening? Now because of the pre-stressing force. Uh, Before that, because of the self weight of the structure, in this zone the structure will sag and uh, will have some vertical downward deflection of the structure because of the self weight. And similarly, because of the SID, we again have some downward deflection. But then we have pre-stressing at the bottom fiber, which will cause the structure to hog up. So effectively, we are having, in this particular case, we are having overall upward deflection due to dead load, SIDL, and pre-stressing. Now the effect of the creep will be to take this upward deflection further upward. So that is why we are casting the stitch segment, or actually other segments as well, below their level. So that because under the effect of the creep, this structure, the the tendency of this zone will be to go upward. So after the desired time, let's say after 20 years or maybe 30 years, we'll have the perfectly desired layout of the street profile. This zone will come down, this zone will go up. So before going ahead, let's see the analysis or the some of the results in the software itself. So this is a structure in MIDAS civil. The deck or the superstructure has been modeled using the line elements. Piers also have been modeled using line elements. And these are the piles which have been modeled using line elements. And then we have plate elements. We have plate elements for the pile cap. Grade of the concrete is M55 for most of the segments, the ones which have been highlighted, and then M60 for few segments, 4 number of segments. We have defined time dependent property for creep and shrinkage as per CBF5P. So this is a creep coefficient graph as per the time, and similarly shrinkage strain graph as per the time for M55 grade of concrete. Similarly, we have how the concrete is gaining the compressive strength with time. This also we have defined as per CBF5P code. We have provided uh, these point spring supports, with the help of which we have tried to model simulate the condition of the soil. So the lateral springs for the along the longitudinal and the transverse direction have been modeled. Earthquake analysis, we have defined this response spectrum graph in the software itself. Now because of the twin pier, we have provided enough flexibility into the in our structure. So the modes, the first mode or the second mode of the structure will not be in this zone, it will be somewhere in this zone. So with the help of, when we provide the flexibility to the structure, we bring the structure from this zone to this zone so that the seismic forces are actually reduced. We have performed response spectrum analysis along uh, longitudinal direction, transverse direction, or also vertical direction. Moving load analysis. So these are the two lanes, lane 1 and lane 2, and vehicles also we have defined 17-ton vehicle in the software itself. Now coming to the construction stage analysis. Now this is stage 1. So these are the temporary support, which are actually compression only springs. Now this is stage 1 where we have cast only the end support. Now after the concrete has gained its strength, we are stressing cable number 1 and cable number 12 one by one. So concrete has gained a strength of let's say in case of the end span 10 days, because the entire end span cannot be cast at one go, we have to cast first, let's say, soffit, then web, and then the deck. So we have taken the time of 10 days, but rest of the segments, the cantilever segments, we have taken 7 days cycle, or total 10 days cycle, 7 days for the concreting, for concrete to gain its strength. So after the concrete has gained its strength, we are stressing cable number 1, so which is from end of the pier to this part. After that, we mount the form traveler. So this is a form traveler. So this is a form traveler, and then we cast the next segment. Here we can see we are casting. We are first putting the form traveler, then we are putting the wet concrete of the next segment, which we are going to cast. So after 10 days, so we are using the casting the segment at the 4th day, and after 10 days, the stage number 3 is starting when the segment S1, the first segment, is activated with the age of 6 days, and then we are stressing the cable number PS2, and then moving the form trailer and the again casting the next segment. So going to stage number 3, the form traveler has been moved, and we've also cast now cable number, stress the cable number 2. So we have stressed cable number 2. Cable number 3, and so on. Finally we reach stage number 12, just before the casting of stitch, and finally we put the suspender and cast the stitch segment, and we reach the stage number 13, and then we are stressing all the bottom cables. So these are all the bottom cables. Now let's see the results one by one. Let's go to stage number 2, and let's check the stresses. So we'll see the stresses due to summation. Now this summation will include the effect of dead load, the erection load, which is actually our construction load, the primary effect of the tendon, the secondary effect of the tendon, the secondary effect of pre-shrinkage. That is summation. So at the top fiber, when Newton MPa, so this is at the top fiber, and then bottom fiber. Now if we go to min max, here we'll see the envelope of the stresses for our entire superstructure. So summation maximum value of the stress at the top fiber, that is maximum tensile stress. So we have no tensile stress at the top fiber anywhere, and at the bottom fiber we have tensile stress of only 0.31 ampere, that too on the pier itself, which can be ignored. Coming to the post-CS part, checking stresses due to the normal load case at the top fiber. This part, and this part can be ignored. So we have a residual compression of 1.202 MPa, the top, and the bottom we have 0.87. Now we can see the tendon loss in the tabular format. Now let's see cable number 1 at the last stage. So we can see the stresses after immediate loss, which will include the anchor slip, then the friction loss, then the elastic deformation loss due to other loads such as self weight and other cables, creep and shrinkage loss at the stage that we are selecting, relaxation loss, and similarly we can see these losses for all the cables. Now this is the effective tendon force for cable number 10, one of the cantilever tendon. So as I told you, this cable has been stressed from this end, and then this fall is due to because of the friction loss. Now let's see the effect of the bending moment, the live load. We'll go to results. We go to moving load tracer. We'll see what causes the maximum bending moment. Let's say at the mid span. So these contours that you see here are the influence line diagram, and the loading is as per the influence line diagram. So this is a vehicle which will cause the maximum bending moment at this zone, and similarly for the shear force Fz at this part near the pier. Sorry, that will be minimum. So going back to our presentation, now this is deflection, deformation due to normal case after 120 years. Normal case means all the permanent loads plus live load. Now this deformation in the upward direction is because of the effect of creep. Now as a result, some of just sharing with you some of the figures just to put the things into the perspective. Total volume of the concrete for the superstructure that we used is 836 cubic meter. Total weight of the tendons that we could optimized up to was 32.425 ton, and which came out to be tendon per unit volume of the concrete was 37.98 kg per cubic meter. Now this ratio actually varies from let's say 35 to 45. So we can rightly say that our design was optimum design. So that is all from me about the design of three-span continuous PSC box girder bridge, which was cast using the cantilever construction technique. For any technical query, write to technical, so you can write mail to technicalsupport@midasIT.com. Thank you for attending the webinar. Bye bye. Have a nice day.